So this is part 2 of the video series with functions and graphs. So we're going to continue with some linear function context problems, and then we'll get into different graphing techniques, looking at Desmos, looking at a graphing calculator, and just looking at ways we can use the technology to give the students a visual. So in this case, we've got the 4th grade class. They're looking for raising funds for a trip. And they want to go for 8 weeks, and their intent is to get to $750. That's their goal. Well, after 2 weeks, they raised $180, and after 5 weeks, they raised $540. So this would be kind of a classic. You're trying to figure out the rate of change. You want to find your slope. You want to write an equation to model this. So the slope, remember, that is your difference in your y values divided by the difference in your x values. And so when you do that, you can start with, it doesn't matter which y value you start with. I notice it shows y of 2. So you can start over here at 540 if you'd like. So we could say 540, subtract 180, and then come back and grab the 5 and the x and subtract the 2. So the 540, take away 180, you're going to get 360 divided by 3. So this is your slope, your rate of change, and that would simplify to be 120. And so that just means that $120 at that rate. And so if you have y equals 120x, you can substitute 8 in for, and so 120 times 8, you'd end up with 960. You would certainly meet your goal of 750. Next problem, you've got Rose took a cab from the airport home, and so we're looking at a cab simulation and a fare, and so she gave or paid the cab $38.50. Now what did that involve? It involved a tip of $5, and it involved the fare. Now the fare was actually $3.50 for the first mile, so that's a constant value, plus $1.50 for every additional half mile. So these you cannot simplify because they're not like terms, and you certainly can't distribute the 5 to both because of that addition sign. So we don't want to make those mistakes there. So we're just going to rewrite, and this will be 5 plus the other constant of $3.50 plus $1.50x. These are like terms, so those are the constants that we can add together to get an $8.50. And then we're just going to use inverse operations, and we're going to subtract the $8.50 from the $38.50 to get $30, and then we would divide by $1.50. How many $1.50s will fit into 30? And that would be 20. Now remember what x represents. X represents additional half miles. So if there's 20 half miles, then there's going to be 10 full miles plus the 1 that she was charged for, is that $3.50 for that first mile. So 10 plus 1, you're going to get 11 full miles from the airport. Next, let's look at some intercepts. And so when we think about intercepts of a linear function, we're talking about where it crosses the x and the y axis. So the x and the y intercepts are useful. It can help us identify some things in context when you're dealing with the x and y axis. And you have a graph. These would be considered, this would be considered your x-intercept, and this would be considered your y-intercept. Notice it's the points that cross the x and y axis. Now your x-intercept is going to look like this. It has some x value and the y value will be 0. And then your y-intercept, notice you'll have 0 for your x and some y value. That could be either positive or negative for the y. That would be either positive or negative for your x. So here's a question that says, defined by the equation 5x minus 3y is equal to 15. Which of these four properly describe what's going on? So what we're going to do is do an x-intercept method and a y-intercept method. All this, what I mean by method, that we're just going to solve and figure out the intercepts. So if I want to find the x-intercept, I actually want to find out what x is, so I'm going to substitute y for 0. So this goes to 0. I'm left with 5x is equal to 15, so I know x is 3. So 3 comma 0 is your x-intercept. And then I come over here and find the y-intercept. Well, that just means that x is going to be 0. And so that goes to 0. I'm left with negative 3y is equal to 15 divided by negative 3, and y is going to equal negative 5. So 0, negative 5 would be the y-intercept for this equation 5x minus 3y equal 15. So this is what your line would look like. So the y-intercept is 0, negative 5. This is what this is asking. Is that true? No, that's a false statement. So that's not going to work. The x-intercept is 3, 0. Yes, that is a true statement. We found that. And then the graph has a slope of 5/3. Well, when you look at this graph, notice that it's going to have a rise that increases and a run that increases. Well, that can be looked at as a rise that increases and a run that increases. So a positive value divided by a positive value is positive. So it's not going to be A, because A is representing something negative. So when you calculate your slope, is it 5 divided by 3? Is the change in y 5? 1, 2, 3, 4, 5. It is 5, and the run is 3. So 5/3 is a correct statement. So 2 of those are correct. 2 of those would be incorrect. Now let's look at a system of equation. Remember, a system of equation is just more than one equation. If you've got 2 variables, you need to have 2 equations to solve it. If you got 3 variables, you need 3 equations, and so forth. And they're both in standard form. So we certainly could solve this by elimination, and we can also solve it by using your intercepts. So we're just going to look at our intercept method for both of these. So the x-intercept would be, we're solving for x. 0 is substituted for y. That goes to 0. X is 4. So then I'm going to substitute 4 back to this equation to figure out y. So 4 plus 2y is equal to 4. So when I subtract 4, I'm going to get 2y is equal to 0. So that means y is equal to 0. So there's your x and y intercept for the first equation, which would be 4, 0, and 0. Let me back up there. I know on this first equation here that an x-intercept of 4 is 4, 0, and the y-intercept So I just established the fact that when x is 4, y is 0, and I'm going to come back over here and now look at the y-intercept of this equation. And so when x is 0, what is the y-intercept? And so this will be 2y equal 4, so y is equal to 2. So 0, 2 is the y-intercept for this first equation. Now let's look at the second equation. And I want to find the x-intercept. So I'm going to have negative 3x plus 0 is equal to negative 3. So negative 3x is equal to negative 3. So x is 1. So 1, 0 would be the y or the x-intercept of the second equation in green. And then what would be the y-intercept? Because this one was the x-intercept. The y-intercept would be negative 3 times 0 plus y is equal to negative 3. So this goes to 0 plus y. So y is negative 3. So 0, negative 3 would be the y-intercept. And we would see that it would intercept somewhere around 1, 1, a little more than 1, and a little more than 1 on the y as well. So that's using intercept methods to, once you find your intercepts, then you just connect your point. You connect those points on a line, and then you can see where they intersect. All right, moving on to talking about quadratic functions. So we looked a little bit at linear. So now let's look at when we're graphing quadratics. And you're going to find quadratic standard form is in this format. And so when I talk about the a value, this is the coefficient of what we call the leading coefficient. And there's the coefficient of the middle term. And then I'm going to include the sign because it could be minus c. And so that would be your c value. And that's going to come back into play when we start talking about the quadratic formula and how we solve that. So the graph of a quadratic equation, it's also called a parabola. Sometimes you'll hear it called a parabolic function, quadratic model, a parabola, a parabolic function. Those are all different forms. Now, when the coefficient is negative, that leading coefficient is negative, you're going to see that graph open down. It's going to look something like this. And when the coefficient's positive, the graph is going to open up. So when that a value is positive, you'll see that a graph would open up. And when the coefficient takes on the value of a very small number or a fraction, or you might see it in a decimal notation, well, then that graph's going to be really wide. You're going to see the graph look like this. And when the coefficient takes on a very large number, like a 5, a positive 5, or even a negative 5, or a positive 10 or a negative 10, you're going to see that graph become narrow. So it could, really skinny, or it could be very skinny opening down. It could be very wide opening down or very wide opening up. So these are some examples. Notice that the coefficient is just a -1. So we would say a is -1, and that indicates the opening down. Here we see, well, we don't really see a number, but we understand that that's going to be when a is 1. And so we see a is positive, so it's opening up. The blue, you see 5x squared, so you see that a value being a positive number and an integer and something larger than 1. So you're going to see that a little bit more narrow. And then you'll see in red the 2/10 x squared, or the the 1/5 x squared if you wanted to write it as a fraction. So both of these coefficients are less than 1. So when you have that, you're going to see it become more of a wide spread opening up or down. And with a parabola, it's going to have what we call a vertex point and an axis of symmetry. You're going to find symmetry as part of a quadratic, that parabolic shape. And it's going to be able to, there will be a vertical line with a parabolic function. You'll see a vertical line that will break the parabolic shape into two halves, but where that line crosses that parabola will be right along the vertex as well. So the vertex is the minimum value, but it's the minimum value when A is positive. And it's the maximum value when the graph is in this form, negative ax squared. So notice what happens when A is positive and when A is negative. And the axis of symmetry is a dashed line. You'll typically see it as a dashed line. It separates the parabola into two halves. So it would look something like this if it was opening down, and you would see, we can even dash it. And it looks something like that, where it splits the parabola into two halves. All right, so this first one, we want to look at how we can find the intercepts. We want to look at how to find the axis of symmetry. So we're going to not worry about this one right now. We're going to look at this first one, x squared minus 2x minus 3. So in order to find the x-intercept, you're basically factoring it if you can. Try to factor it, and then you can find your solutions. So x squared minus 2x minus 3y, I'm setting it equal to 0 because I'm trying to figure out the solutions or the zeros to this function. What value of x will make the y value go to 0? That's what we want. So can I factor it? So I'm thinking of two numbers that multiply to give me negative 3, but add to give me negative 2. Okay, that's going to be negative 3 and a positive 1. And so since a is 1, I'm just going to take my values from these two and set them into my factored form. And then I'm going to set each of these linear pairs equal to 0 and solve. So x is negative 1 and x is 3. What does that mean? Well, that means that 3, 0 and negative 1, 0 are your solutions. So there's 3, 0 and there's negative 1, 0. And now I need to find the axis of symmetry, which is this equation right here. Now a, from my formula, from my equation, a is 1. It's that understood value in front of the x squared. B is negative 2. Notice I'm taking the sign with the middle term. And then C is going to be negative 3. Same thing. I'm going to take the sign of the C. I mentioned earlier that can be, if it's an addition, then it's going to be a positive value. If it's subtract, it's going to be a negative value. So x is equal to negative b, and b is negative, multiplied by 2 times a. So since b is negative, when you take the negative of it, you're going to be positive 2 divided by 2, or x equals 1. So you're going to see, let's go ahead and do that dashed line at x equals 1. That is your axis of symmetry. And now the vertex. Well, the vertex can be found in different ways. Okay? One way is you can substitute it back into the function. Substitute it back into the function to figure out, well, what's the y value? Okay, well, it's going to be 1 squared minus 2 times 1 minus 3. So this is going to be 1 minus 2 minus 3. So left to right, that would be 1 minus 2 is negative 1. Negative 1 minus 3 would be negative 4. So at 1, negative 4 is going to be the vertex. And so it would look something like this with the sketch. Now I'm going to show you a couple of different tools. One is a free online tool that we'll bounce back and forth to in this video, and it's called Desmos. Desmos.com is a free graphing calculator. So I'm going to type in the equation. So I'll just type, as I'm typing on my keyboard, y equals, and I'm going to type x, and then I'm going to hit Shift 6, which takes me to an exponent, and that'll be an x squared. And then it's minus 2x minus 3. There's the graph from what I just gave a sketch of earlier on our notes. And then you can see right down here at 1, negative 4, that is that minimum value. And so this vertical line that runs all the way up here will be x equal 1. Notice it shares the x value of the vertex. So at x equal 1, if x equal 1 is the axis of symmetry, then that means the vertex is going to have 1 in the x value. The y value will be different. It'll be the result of what you get. So notice I go back to my equation and I open parentheses and I put a 1 in and delete the x, and then come over here and put a 1 in here and delete the x. Notice what the calculator gives me as an evaluation. It gives me negative 4. So 1, negative 4 would be where your vertex would be located. Now you also have another. It's called your, this is a TI-84 version. It's my calculator, my computer calculator version of a Texas Instrument 84 Plus. So if I go to y equal up here, I'm just going to type in x squared. So over here, my cursor on the calculator, so x squared, and then it was minus 2x minus 3. Notice this button over here is your minus. This button right below the 3 and to the left of enter is for your negative. Now, if you graph that, you're going to see the same type of graph. And if you go to second graph, you look at your table, notice that first point is at 1, negative 4. Now, we also solve for x-intercepts, remember? So notice 2 of our answers for our x-intercepts was 3, 0, and negative 1, 0. And here they are on the graph, negative 1, 0, and 3, 0. So anytime you see y values as your anytime you see 0 as your y values, then you know that these would be your solutions. You may not always see them on a graphing calculator, especially if you have your own, or if you have the students using it in class. These are just things that you identify. These would be solutions, also called x-intercept, also called zeros of. So let's go back and go back to my whiteboard and our notes, and let's look at second equation. And I think I'm going to tweak this second equation for just a second. I'm going to give us another equation to look at. All right, so I'm going to change this. Let's look at a different equation. Let's look at y equals negative 3x squared plus 15x minus 18. So what I want to do here is I want to factor it. So this negative 3x squared plus 15x minus 18 equal to 0. So I'm going to factor out a negative 3. I already know that this is going to open down because what indicates that? That's right, the a value. Since a is -3, you know this is going to open down. But I'm going to factor that out, and that's going to give me -3x squared divided by -3 is x squared. 15x divided by -3 is -5x. -18 divided by -3 is a +6. So now I want to factor this. I'm looking for factors that multiply to give me 6 because a is 1. 1 times 6 is 6. Two factors that multiply to give me -5. So that's going to be a -3 and a -2. Those both add to -5, and they both multiply to give me +6. So since a is 1, I'm just going to pull from right here, x minus 3, x minus 2. So this -3 is just a factor. So I'm going to have x minus 3. Let me just pull this down here. X minus 3 is equal to 0. X minus 2 is equal to 0. So x could be 3. X could be 2. So 3, 0, 2, 0. These are going to be really close together. And it's going to be kind of a skinny graph, narrow, because of the -3 as the coefficient. And then my axis of symmetry, that's going to be negative. So A, let's go back up here and list A, B, and C. A is -3, B is 15, C is -18. So with your axis of symmetry, you're only dealing with A and B. So I'm coming over here and using this equation, x equal -b divided by 2a. So -b, b is 15 divided by 2 times a, which is -3. So x is equal to -15 divided by -6. And that is equivalent, they're both negative. So 15 and 6 can both be divisible by 3. So 5 halves. So that would be the same as 2.5, which makes sense. 2.5 is going to fall right between the 2 points here. And so that would be your line of symmetry. If we were able to draw it just right, it's kind of a smaller graph right there, but we know that that line is going to fall right between those two values. And we know that it's going to open down. So what would be my vertex? Okay. Now you can, of course, use x equal 2.5 and just substitute 2.5 in wherever you can. Okay. I always encourage the students at this level, you can use a graphing calculator, and then they can pull the points from the technology. So I'm going to go back and go to the Texas Instrument here. I've got -3x squared plus 15x minus 18. I'm going to graph it. You're going to see it starting to look exactly like what we had on our graph. If I go to second graph, I'm also going to see the two intercepts that we found at 2, 0 and 3, 0. But I don't see 2.5. But if I go back to graph and I use trace, I can type in 2.5 for my x and hit enter, and it's going to tell me exactly what the y value would be. So it'd be 3/4. So 2.5 would be the x value, and 3/4, which is 75 hundredths if we stayed in decimals, would be the y part of the vertex. If you did the same thing and you went to, let's say we went to Desmos, and we have y equal -3x to the second power, so that's -3x shift 6 squared plus 15x minus 18. So you can see there's the graph, and if I put my cursor right there at the top, you'll see it's 2.5 and 75 hundredths. That would be your vertex. And notice the 2.5 is what we found as the axis of symmetry. So let's switch gears and let's look at absolute value functions. The absolute value function, this parent function, what sometimes we'll call it parent functions. A parent function of a linear equation is y equal x. A parent function of of a quadratic would be y equals ax squared, and then a parent function of your absolute value would be the absolute value of x. That just means that everything stems from that parent. Now we can translate it and figure out different transformations by different forms of the parent function. So the standard form for a parent function, or for a standard form for an absolute value equation is what we see right here. So that a value is going to tell you the slope of the line of the V. We're going to see this is going to be a V shape. And each side of the V is going to have a slope. One's going to be positive, one's going to be negative, but it's going to have the same slope. And A also tells you how wide or how narrow that V shape is going to be. And so it can be pretty skinny or it'll be fairly wide. And the B part of this, the B value, will tell you where it's going to shift. Is it going to shift, it's going to be either left or it's going to shift right. And what we'll notice is if B is negative, the V will shift to the right. And if the B value is positive, the V will shift to the left. And then C just tells us the vertex. It's it's where the two sides of the V will come together, and it will be a vertex. We have a vertex with a quadratic. We have a vertex with an absolute value. And the C value tells whether the vertex is up or down from the x-axis from 0, 0. So let's take a look at some of these here. We'll notice with the absolute value of x minus 4, it's going to be very similar to the parent function, but this -4 part of the C value is just going to drop it down 4 units from the origin. And since A is understood to be 1, notice I'm putting the 1 out front, that's your A, it will have a slope of 1 to 1 on both sides, positive 1 to 1 and negative 1 to 1. So we should see something that looks like this. And that needs to be a solid line and not a dotted line. Now the second one is also part of the parent function, y equals absolute value of x, but it's going to increase 4. So this C value is positive for us, so we know it's going to move up from 0, 0, but we also have a negative A. So this is going to, from here, we're actually going to have a negative and a positive, and it's going to be a reflection. So it will look as a V shape, kind of opening down because A was negative. Over here, we're seeing that it's opening up. This one where it's opening down, all that has to do with what your A value represented. Very similar to the quadratic. Here we've got, in this form, we see that it's going to drop down 3 from the origin, but this is, remember that original form was A times the absolute value of x plus B plus C. Well, if B, now notice that this is x minus, well, that means B had to be negative, so we're going to see this shift to the right 1 and down 3. So there's our new vertex. And since A is 1, then we know that we're going a 1 to 1 on either side there. And this is what's just a transformation. It moved to the right 1, down 3. So this is your vertex of your absolute value graph. Over here, we see that it is, the A value is negative, so we know it's going to open down. Here we see B is positive, and we said that if B was positive from the notes earlier, it was going to move left. So we're going to see this graph move left 3 and up 3. And so there's your vertex. Would be -3, 3. And A is -1, so we know that we're going to be a 1-to-1 on all of these, and it's going to open down. Let's look at exponential function. This is a special function that shows rapid change, that changes that are non-linear. So we've had some linear pieces to the absolute value. We've had linear functions we've talked about. Quadratics would be non-linear. Exponential graphs are going to be non-linear. Sometimes you'll see the exponential graphs grow slightly. It's a slow change, but still non-linear. You may see it either grow, or you'll see what we call it as a decay. Here is your a times b to the x. That's your general parent function for your exponential. When we add a c value to it, we're actually, the c value is going to represent what we call an asymptote. It's just a point to where the graph will, you'll see it be an approaching, a limit, kind of an approaching to this line, and that c value will help you understand where that's going to be. The a value is your y-intercept. This is your asymptote line, which will be horizontal. The b value is going to tell you one of two things. It's either going to tell you, well, if b is greater than 1, you know you're going to have a growth factor. You know it's going to increase. If b is less than 1 but bigger than 0, then you know you're going to have a decay. All this means right here is if you see a fraction, you see a decimal, you know that that graph is going to decay. Oh, let me back up. I did fill that in. So A represents the y-intercept, and B is going to represent the growth or decay factor. These are all examples of exponential growth. Notice the shape of them. You're going to see that type of shape kind of when the A value is positive and our B value is larger than 1, then we're going to see it grow from left to right. Notice the equation g of x is equal to 2 to the x power plus 3. Notice this plus 3. There's your asymptote. But notice the y-intercept. Notice the y-intercept, you're looking at it here and you're thinking, well, wait a minute, it just went through 1, but over here it's understood to be 1. Well, what's 1 plus 3? Well, the y-intercept was at 1, but we're shifting the graph up 3. So now 3 plus 1 gives me 4. That's my new y-intercept with the asymptote line at x equal, or y equal 3. Notice the base is 2, so that is larger than 1, so we are going to see it grow. Notice the middle one here is y equals 2 to the x power. Well, that's really the same as y equals 1 multiplied by 2, raise it to the x power plus 0. We just don't write the 1 many times. If it is 1, we just won't write it, and we won't, if it's the horizontal asymptote is 0, we just won't write it. So when you see y equals 2 to the x, it just means that the horizontal asymptote is at 0, and it should go through 1 on the y-axis. And then here you've got y equals 2 to the x power minus 3. Understood a y-intercept of 1, but if we drop it down 3, we're going to see our y-intercept at -2. But we also see the horizontal asymptote at y equal -3, which was identified right here. Next one, you see the graph goes in the opposite direction. So it's what we call a decay graph. And so this is either going to be decreasing by a certain percentage. So if you get 1/2 here, that just means that we're decreasing by 50%. So if we take 100%, subtract 50%, we're going to get 50%. That is going to be your growth, your decay factor. Notice everything's going to have a y-intercept of 1. We're just adjusting our decay value. So if this is 1/3, then that just means that we're decreasing by 2/3. And then the other one is we're decreasing by 90%. So our decay value would be 1/10. This one would be 33% roughly, and they all go through the y-intercept of 0, 1. And notice they all are hugging this y equals 0, because notice all of these graphs have a +0 at the end. So that's why they all have that same horizontal asymptote of y equals 0. Now this next graph, we're looking at f of x is equal to 3 to the x power. So remember, this has an intercept, a y-intercept of 1, a base of 3. We know it's going to grow, and a y-intercept or a horizontal asymptote at 0. So that's really kind of what it looks like. We just left off the 1 and we left off the 0. Now here's what we want you to do. We want you to reflect it over the x-axis. So we know this is going to look something like this. We want to reflect it over the x, and we want to translate it 5 units to the right. So I want to shift gears to, let's look at Desmos. And so if I have y equals, I'm going to type y equals, and then 3, and actually I'm going to type in what the parent function is. It's 1, open parentheses, 3, close parentheses, shift 6, x. And I need to arrow over, and I'll write +0. Now I don't have to do that. Of course, I can leave the 0 out and the y off, or and the 1 off there, and then you can see, well, there's your y-intercept of 0, 1. And this, what you'll see is over time, this number is approaching zero. Every number on the x is going to then approach 0 on the y. Now, if I want to reflect it, so I'm just going to add a different equation so we can see. If I want to reflect it, in order to do that, I need to write a -1, open parentheses, 3, raised to the x power. And so notice that the -a reflected it. But I also want to shift it to the right. So I want to see this y-intercept right here at 0, -1. I want it to move to the right 5. So I want to see this point right here move 1, 2, 3, 4 to right over here. And in order to do that, I need to make my change in my exponent. So I'm going to put parentheses around the exponent, which is just shift 9. -5, did that do it? That does shift the value, and of course this scale is not, if I zoom in, you'll see what happens when I shift it. So I want to move it, here it is at 0, I wanted to move it 5 to the right. So there's 1, 2, 3, 4, and there it is, it's 5 to the right. So it was at 5, -1. So it is reflected, and what equation, so you're looking in your notes, which equation would model this reflection, and that would be g of x is equal to and then base of 3 to the x minus 5 power. Now what Desmos will do is definitely give you a good sketch. If you want data points, then what you need to do is evaluate it. Now I'm going to show you both ways using this and the graphing calculator, because you might have your own graphing calculator, and I want you to understand how you can utilize that. So the next part of the notes is looking at sketching two graphs. So y equals 4, open parentheses, 2 raised to the x power. So I'm just going to come over here on Desmos and hit this home screen, and that's going to take me to looking at this. Now what if I want to create a table? Well, that just means I want to come up here to the x, open parentheses, and what am I going to get when I put in -1? So you see in the box here, it tells you what it would be. So when x is -1, y is 2. So you can start to build your data table. Now what happens when x is 0? Well, we know that because it's a 4, because the 4 is a. What happens when x is 1? You see how it's changing. So I'm just making my changes in the exponent. What happens when x is 2? I get 16. What happens when x is 2.5? Notice you get another type of decimal. Now if I wanted to do the same thing with the graphing calculator, I'm just going to go to y equal. I'm going to clear out what I see there. And I'm going to type in 4 and then open parentheses 2 raised to the x power. And then I'm just going to go to second graph and look at my table. So here I've got all the different types of values. If x is -4, look, I have 1/4. When x is -2, it's 1. When x is 0, it's 4. When 2, it's 16. So that's another way to create a table if you have your own graphing calculator. It's typing in the equation in y equal, and then go to second graph to pull up your table. So that's what I always encourage my students to do when they're analyzing a graph using the technologies. Use the technology to your advantage. You don't always have to do a substitution and do it by hand. We have the technology that'll create and make that faster for the students. It allows you to talk about the graph, talk about analyzing it instead of spending all the time doing the computation. So I'm just going to work backwards. I'm going to go to another equation here, and then I'll go to Desmos. So y equals 2, open parentheses, 5/10, close it, raise it to the x power. Notice this button just above your division bar is what you're raising it to. So when you click that button, then you can pick the variable as an exponent. When I graph this, you're going to see it go the opposite direction. What caused it to do that? It's that b term. The b value is 5/10. So it caused it to decrease. And then second graph will take you to your value. So you can even see the visual of your y values decreasing and getting into the decimal values as x is increasing. So you can use this to fill in a table, or if I ask you on homework to create a table, you can use your graphing calculator to do that. Or you can go back to Desmos. If you don't have a graphing calculator, it's not a big deal. Go to Desmos, go to y equal, and then we'll type in 2, and then shift 9, and then 1/2, or you can use 5/10, arrow over, close it, shift 6, takes me to the exponent, and there's your graph. Same one that we saw in the graphing calculator. So if I want to input values for x, I'm just going to need to put parentheses around the variable. So shift 9, and then if I do a -2, I want to delete the x, go back to shift 9 or shift 0 and close it. And then notice it gives me a value for it. So -2.8 would be one value to go in your table. If I go to -1, you'll see it's 4. I'm just hitting backspace, 0, it's 2, backspace, backspace, 1. 1, 1, backspace, 2 is half, 3 is quarter, 4 is 1 and 2500ths, and we saw that pattern of decrease in the graphing calculator as well. So those are the things that you start to notice differences in exponential decay, which is what you see here on Desmos, and then something that looks like that, and we see that the 2 value is showing a growth in the purple graph, and 1/2 is the decay factor in the green. So I hope that was helpful. That's the end of part 2 for our series on functions and graphs.